Let's see what is Bolzano-Weierstrass theorem. Every bounded sequence of real numbers has a convergent subsequence. This is the idea for the method 2. So before going into it, I'll just read out what is it, the method 1 is about. I'll just give you an intuitive idea because I have already shown the proof of monotone subsequence theorem and monotone convergence theorem. So monotone subsequence theorem statement is every sequence has a monotone subsequence. So from this I got a bounded sequence. So sequence I have got. So there is a monotone subsequence. So I can say this sequence will have a monotone subsequence and it is bounded. So I know a theorem called every subsequence of a bounded sequence will be a bounded. So I got a bounded monotone subsequence from this itself. So bounded monotone subsequence I have got. And I know a theorem, monotone convergence theorem. So you can watch it. The statement goes like this: every monotone sequence, it is bounded if and only if it is convergent. So that is what is here. So given a monotone sequence, it is bounded if and only if it is convergent. So I have a bounded monotone. So monotone bounded I have got. So it implies it is a convergent. Since it is for sequence, I am going to say it for a subsequence because subsequence is again a sequence. So I can say, on the whole, I can say that the thing that I am got, that is the subsequence that I got, is a convergent subsequence. So here the theorem ends. This proof is simple because you should know these two theorems. So in order to prove the second way, we have to know Cantors theorem, and in the Cantors theorem we have to know sandwich theorem, and obviously you should know monotone convergence theorem. That one is common for both of the proofs. So let's see what is Cantors theorem first. Before going into it, let us make it clear. I'll just say the hint for the Cantors theorem. Cantors theorem on nested interval. So you don't want to worry about all these things because you have already proved in the one way. So I'm just going to go for the second way. And Cantors theorem is simple, and I have to say you the hint, right? So hint goes in the first hint should be, you should know the statement of the theorem, because Cantors theorem, we should know the statement first, because in every theorem you should know the statement. So first hint will be that. So I'll write the statement over here. I have to have a closed interval an comma bn, and that interval is varying up depending on the n belongs to natural number. It is a sequence. So we saw so far sequence in like an something like that, but here sequence of closed intervals. So closed intervals such that these two conditions getting satisfied. It is very simple. an plus 1 comma bn plus 1 is contained in strictly contained in an comma bn, because here I'm just shrinking the interval, so obviously it will be strictly contained in. Okay, so where for all n in n, and I'm going to denote delta, which is the length of the each interval. So that is nothing but delta n, because it depends on the n. So here the length will be bn plus 1 minus bn plus 1. Here the length will be bn minus an. So it varies. So I have to vary this length also. So here limit n tends to infinity, delta n should be equal to 0. That is, I am shrinking the intervals again and again, so far if till I am getting 0. So this is what I should reach, where del n will be bn minus an. It's just a notation. So del n represents bn minus an, which is equal to length of the interval. You have to write which is equal to length of this interval. Fine. If these two hypotheses getting satisfied, then my intersection where n equal to 1 to infinity, because I am intersecting all the closed intervals. So if I am intersecting all the closed interval, that is an comma bn, I have only one element, contain precisely one element, precisely one point. Okay, so this is the idea. and you can, if you want geometrically, I can show it. Let me show you with an example. 1 by n comma minus 1 by n comma 1 by n. Obviously this is the ultimate example that we use in everywhere. So in order to, what we can say, okay, let's add 1 to it, okay, because you have seen minus 1 by n and plus 1 by n so far. So let's just try it over here. 1 minus 1 by n and 1 plus 1 by n. So I'll write first element would be 0 comma 1 plus 1 2. So this is my first a1 comma b1. According to my hypothesis, a1 comma b1 should contains the second closed interval, that is a2 comma b2, like this. Okay, so if I put 1 by 2, I will be getting 3 by 2. You can know this is 0.5 and this is 1.5. So this is containing inside this. So it goes on, and hence I am getting limit n tends to infinity, del n should be equal to 0. So if I am intersecting, not intersecting, so if I am stringing over and over, so my first interval would be 0 to 2, 1 over here. Okay, my second interval will be like this, and it goes on because I'll just show it over here. So it goes on, and ultimately I'm going to stop at this 1. So it goes on, and my intersection point would be intersection of a n comma b n would be 1 only. It's not it is actually only one single element, okay, precisely 1 point. It cannot be more than 1. So that is what the idea is. As I mentioned earlier, Cantors theorem needs sandwich theorem and monotone convergence theorem. So don't worry, in the Bolzano-Weierstrass theorem you are going to construct this type of interval, and you will be saying it has only one point. So, and that is why from there the proof goes on. So you just need the statement alone, but during the interviews they would also ask you to prove the Cantors theorem, because you are using the Cantors theorem in your proof. So obviously you should know what is Cantors theorem. So that's why I am proving over here. Idea is something similar to from the hypothesis you can take. That is, I am having an and bn. Let me take this as a an and this as a bn. That is what it is, right? So an and bn. So it would be an plus 1, bn plus 1. So I'm just telling the proof, okay? So my 0 is my an, and half is my an plus 1. 3 by 2 is my bn plus 1. 2 is my bn. You already know this, right? So I am going to get a relation here. That is hint. I am going to say the hint. The first hint would be an is lesser than or equal to an plus 1. I think I don't want to write this lesser than or equal to, because it is strictly contained in, but anyways I can write, because you have to go for infinite terms, right? And it is bn plus 1, which is less than or equal to bn. This one you obviously know from this. From this you can understand, and this is what it comes. So I can extend this for a1, a2, a3 and all. So extend the above. Extend above for all n. Then I can use monotone convergence theorem. I can write monotone convergence theorem. Monotone convergence theorem is nothing but if it is monotonically increasing and bounded above. So if you can write also there is a relation between an plus 1 and bn plus 1 also. So you should not miss it over there. Okay, I should write this also. And also an is less than or equal to bn. How you got an is less than or equal to bn? In the closed interval, this one is obviously less than or equal to this one. So I'm saying equal to won't come, but in order to avoid, because there are infinite number of intersection, that is arbitrary intersection. So an is less than or equal to bn. So I had a relation, I am going to have a relation a1 less than or equal to a2 less than or equal to goes on an, which is less than or equal to goes on, then bn and it goes on like Bn is a kind of decreasing. You can understand An is less than or equal to An plus 1. It is monotonically increasing. Here it is monotonically decreasing. Okay, that is what monotonic convergence theorem comes into play. Okay, so by monotonic convergence theorem, I can say limit n tends to infinity An equal to L, and limit n tends to infinity Bn equal to M. I'm going to have that limit as, because it is convergent. By monotonic convergence theorem, I arrived at An is convergent and sequence Bn is convergent. So that is this point or converging point. So I'm just taking let. This is just a let, okay, because by monotonic convergence theorem. So this is my first hint, and this is my second hint. This is my third hint. Third hint is unnecessary, but you should know that you are going to use this L and M for the next. Can you understand what you are going to prove? So you have taken this and you are constructed in this way only. So these are the hypotheses. So you have to say intersection contains precisely one point. That means you are going to take the intersection. Then you are wondering why you should know the converging point and all. But you will be surprised by the end of the theorem. I mean, theorem goes in a particular way, like the convergence is necessary for proving this theorem. So I have used the first hypothesis, that is I have constructed so far. So first hypothesis, I have constructed the first line like An is less than or equal to An plus 1, Bn plus 1 is less than or equal to Bn. Also I know if there is an interval called 0, 1, 0 is obviously less than or equal to 1. So that is why An is less than, this is obvious, An is less than or equal to Bn, because in any interval this is obvious. So I have arrived at this, and hence there is a monotonically increasing and monotonically decreasing thing, and hence I can say it is by monotonic convergence theorem, An converges to L and Bn converges to M. So I have used the first hypothesis successfully. So I am going to use the second hypothesis. Okay, so second hypothesis, that is my obviously the second hint. Okay, so second hypothesis says Bn minus An is when it is n tends to infinity, it is equal to 0. So what does it mean? So I can use that. So limit n tends to infinity only, there are limit n tends to infinity. So you know Bn by limit property, if it is addition also goes to L plus M and subtraction will goes to L minus M. Bn minus An goes to 0. This implies L is equal to M. This is by property of the limit, algebraic property of limit. Okay, actually I am writing the hint, but the point is the theorem is going to get end soon. I'm just going by line only. So let me call this L and M as alpha, as the book says. I'm just going, but you can always use a L or M or something. So if I'm going to place this as an alpha, then alpha is the least upper bound of the sequence An, and obviously alpha is the greatest lower bound of this sequence, because by monotonic convergence theorem itself, I am going to say that An is a monotonically increasing and it converges to L, where L is the least upper bound, and here M is the greatest lower bound. But I mean, if you go through the monotonic convergence theorem, you would obviously know that it is the least upper bound and it is the greatest lower bound, right? Yes. So I have named both as alpha. So alpha becomes least upper bound, alpha becomes greatest lower bound. But you know, there won't be like the same number should be both LUB and GLB. So if it is LUB and GLB, then it would be a constant or something. So it is not obviously constant. So it is LUB of AN sequence, and it is a GLB of Bn sequence. So now it is correct, right? But everything is lies on in this relation. Okay, fine. So I have constructed using this as well as this. Now I need to show intersection. So I am going to use the LUB and GLB definition. So that is my second, the next hint for proving this one. Okay, by LUB property, An is less than or equal to alpha for all n, and by GLB property, Bn is greater than or equal to alpha for all n. You should know. You should be careful with the notations. So I'm proving, it's not actually hint. Okay, it is the proof only. The Cantors theorem statement I have written. I have okay. This is just an example. Okay, so the proof. I'm just proving the theorem only. So we almost arrived. So alpha belongs to intersection of an comma bn, because we have got this an is less than or equal to alpha because alpha is the LUB, bn is okay, so greater than or equal to alpha for all n. So for all n it is true, and hence alpha belongs to intersection of an comma bn. So hence we have shown that, actually we have proved that alpha belongs to the intersection. So contains precisely one element, and one point is nothing but alpha, but we have to say precisely, right? So that is what our next aim. So obviously we are going to prove by contradiction. That is beta alpha not equal to beta, which is also belongs to intersection of n equal to 1 to. So let's prove the uniqueness of this by contradiction. So I have taken beta, which is not equal to alpha, which belongs to intersection of an comma bn. So what happens is, I can say this beta will lies between bn and an, right? So since an is convergent to alpha, bn converges to alpha, I can say some un converges to beta. Okay, that is in this way I can say an less than or equal to un, which is less than or equal to bn, and hence by sandwich theorem this converges to alpha and this converges to alpha, this converges to beta, means beta has to be equal to alpha. Thus the theorem is getting proved. So this is the Cantors theorem proof.